we propose Ground Reaction Inertial Poser, or GRIP, physics-based human motion capture from sparse IMUs and insole pressure sensors. Our goal is to reproduce physically plausible full-body motion from minimal sensing. With just 2 smartwatches and 2 smart insoles, GRIP controls a torque-driven humanoid in physics simulation to reconstruct diverse, realistic human movements. Here's an overview of GRIP. It consists of 2 main modules, KinematicsNet and DynamicsNet. Both modules take as input the data measured by wearable sensors. The sensor data consist of measurements from smartwatches on both wrists and smart insoles on both feet. The IMUs provide orientation and acceleration at 4 locations in the global coordinate frame. The insole sensors provide vertical ground reaction forces, center of pressure, and contact labels for the front and rear of each foot. Using these sensor measurements, KinematicsNet progressively estimates kinematic information. It first predicts the positions of 5 leaf joints located at the wrists, feet, and head. Based on these positions, it then infers the full set of 24 joint positions. Next, it estimates full body joint angles, and finally, it predicts the velocities of 6 key joints. These sequential predictions provide the kinematic information required for the subsequent module. State difference represents the kinematic observation that captures the discrepancy between the predicted motion and the humanoid's current state, and it is provided to DynamicsNet as one of its inputs. In addition to this kinematic observation, DynamicsNet also receives sensor observations from the wearable devices, self-observations describing the humanoid's current state, and environmental observations in the form of a height map. Using these combined observations, it predicts target joint angles, which are converted into joint torques through PD control to drive the humanoid in the physics simulator. DynamicsNet is trained using reinforcement learning with the PPO algorithm, where the reward consists of a discriminator reward and an imitation reward. These are examples of the motion reconstructed in the physics simulator. GRIP can reproduce a wide range of behaviors, from locomotion such as walking and jogging, to fast sports movements, slow and controlled exercise motions, and even interactions with objects. However, the humanoid may occasionally fall during motion reconstruction. To handle such cases, GRIP includes a fall recovery mechanism. When a fall is detected, the system retrieves recent kinematic predictions stored in the history buffer and replaces the motion during the fall with these kinematic estimates. After the humanoid is reset to the corresponding pose, the physics simulation resumes from that state, allowing the motion to continue smoothly. Next, we introduce the PRISM dataset that we newly constructed for training and evaluation. PRISM provides synchronized multimodal data from 8 IMUs mounted on the wrists, feet, knees, pelvis, and head, together with foot pressure measurements. It also includes high-precision motion labels captured by an optical mocap system. In addition, Area Glass provides environmental point clouds and head trajectory data, and the dataset contains 3D models of the objects used for human-object interactions. PRISM captures a wide range of human motions. It includes daily activities such as walking and jogging, slow movements like stretching and balancing, and fast sports actions such as golf and soccer. It also contains various interaction behaviors, including motions that involve sitting on objects as well as stepping onto them. This diversity enables GRIP to handle realistic and physically varied scenarios. Here, we present a qualitative comparison between GRIP and several baseline methods. PIP, Global Pose, and Mobile Poser rely solely on IMUs and perform physical optimization after kinematic estimation. Form also uses IMUs and foot pressure sensors on both feet, but it remains a purely kinematic estimation method without physics. In contrast, grip uses 4 IMUs on the wrists and feet, along with pressure data from both insoles, and reconstructs motion through physics simulation. The results shown here represent the first example from the PRISM dataset. While the baseline methods fail to reproduce correct foot-object contact, grip accurately reconstructs the stepping-on object motion. Here's another example from the PRISM dataset. While several baseline methods show issues such as unnatural body tilt, incorrect knee angles, or foot floating, grip reconstructs the motion accurately. Here's an example from the under pressure dataset, which mainly contains locomotion sequences with large global movement. As shown by the root joint trajectories, grip most accurately reproduces the global walking path compared to all other methods. Here's another example from the under pressure dataset showing a jogging motion. Here is a result from the PSU TMM 100 dataset, demonstrating a Tai Chi motion. Grip accurately reproduces the full body motion, even in slow, weight-shifting movements, capturing both upper body motion and detailed foot-ground contacts. Methods that rely on physical optimization, such as PIP and mobile poser, occasionally exhibit unnatural foot constraints caused by contact estimation errors. In contrast, grip produces natural and stable foot contacts through physics simulation. Finally, we present some current failure cases of our method. Typical examples include stumbling or misstepping during object interactions, as well as losing balance when reconstructing challenging motions.